Using the general properties of reaction equilibrium constants. So in this particular kind of question, we've actually been given the value of the equilibrium constant, and we need to infer from that, first of all, what it can tell us about the relative equilibrium position. And then if we look at related chemical equation reactions, if we can derive K for one reaction from K of the reaction that we know. So first of all, looking at the relative value of the reaction constant K, that tells us a lot about the reaction. If K is a large number, so bigger than 1, usually somewhere in the region of like 10 to 100, we would consider to be like large, or obviously greater than that, depending on who you ask, right? So what that tells us is that the equilibrium lies far to the right, which favors the production of products. So obviously, if K is extremely large, then this takes us into the territory of reactions that only really noticeably proceed in one direction, as in the forwards direction. If we have K being much smaller than 1, so that's generally accepted to be in the range between 0.01 and 0.1 or lower, then that's telling us that the equilibrium, really that position lies very far to the left, which of course favors reactants, or if you prefer, that the reaction generally runs more in reverse. That in parentheses for you. So obviously we have a very, very small K. What that actually tells you is that the reaction predominantly runs in reverse. So obviously we have a whole spectrum here. If a reaction is sort of heavily skewed towards the right, then that tells us that there's more products present at equilibrium. If it's more skewed to the left, that tells us there's more reactants. If it's somewhere in the middle, which ALEKS takes as being somewhere between 0.1 and 10 for the value of K, other textbooks says between 0.01 and 1,000 for the value of K. Those intermediate values, what that's telling us is there's products and reactants present at the same time, so you can't say whether it's skewing heavily towards the reactant or the product side of the equation. So in this case, our value of 1.5 is sort of slap bang in the middle there of the range of K, so I would say neither of the above is true. So let me put those values in here for ALEKS. K being large is greater than 10. K being small is less than 0.1. You may find other textbooks or resources that put those numbers at over 100 or less than 0.01, just putting it out there. Okay, so then we're asked for the equilibrium constant for two other reactions below, which are related to the reaction that we know K for. So there are some rules, okay? So these can be derived from looking at generic equation and writing an equilibrium constant for that equation, and then considering what the generic equilibrium constant would be for example, for the reverse reaction, or for the reaction multiplied by an integer. But for now, we can just use the rules. So the reaction equilibrium constant K for a reverse reaction is just the inverse of the equilibrium constant K for the forwards reaction, okay? So just take the inverse. If we have K for a reaction that's been multiplied by some power, which I'm going to call K prime, we can calculate that from K to the power of the integer n that the reaction was multiplied by. So I'll just put my n up there. And lastly, if we have a equation that happens in multiple steps, so you're summing intermediate steps and you know K for each intermediate step, you can calculate K for the total reaction by multiplying K for each of the individual steps, however many there are. Okay, so what are we looking at here? So this is where we're going to play the game of looking at the equation that we know K for and the equation that we're trying to solve for and trying to play spot the difference. So we have the reaction between carbon monoxide and water forming carbon dioxide and hydrogen. And first of all, we're asked about the reaction between carbon dioxide and hydrogen forming carbon monoxide and water. So that's a reverse of the reaction we know, okay? So we're going to calculate K of our reverse reaction by taking the inverse of K for the forwards reaction, which we know. So that is going to be 1 divided by 1.5, stick that in your calculator, and you should get 0.666666. So two sig figs, that'll be 0.67. All right, so what is the other equation we're looking at. So this time we have 2 moles of carbon dioxide plus 2 moles of water forming 2 moles of carbon dioxide and 2 moles of hydrogen. So if we compare apples to apples, we can see that we've multiplied the equation that we were given by a factor of 2. So K for the equation multiplied by a factor of 2 is going to be whatever K was for that original equation raised to the power of that integer that it was multiplied by. So that will just be 1.5 to the power of 2. 1.5 to the power of 2 will be 2.25. So if we were going to round that to 2 sig figs, I think we were asked for, 2.3 would be sufficient. So just a little note on that. If you're looking at the reaction you're trying to find K for, say you divided by an integer, well, you can still do that. So say it was divided by 2 instead of multiplied by 2, then you're just going to work out K prime equals K to the power of n. In this case, n would be 1 over 2. Okay, so if you're dividing by a number, you can still solve that way. Okay, also watch out for if multiple things are being done at the same time. Okay, so if I was asked to calculate the equilibrium constant for, I don't know, 2 moles of carbon dioxide plus 2 moles of hydrogen forming 2 moles of carbon monoxide plus 1 mole of water, well, I have both reversed and multiply by 2. So you can do both of those things. You can take the inverse and you can raise to the power of 2 and calculate the new equilibrium constant. All right,